So the next theory for accommodating the behavioral phenomena for decision under risk will be Gul disappointment aversion theory. I told you about choose weighted utility that it was not very popular today. Well, Gul is different. I think prospect theory is most popular, but then this theory is second most popular for decision making under risk. Big reason is that it's very tractable, as I will explain. You also see quite some risk theories have been developed. And this makes sense. If you have new phenomena, you try all kind of theories to accommodate it. They all have their pros and cons. The time will tell which will be the best. And I think the ultimate best theory hasn't been discovered yet. Maybe it will be a combination of all the ideas that these theories have that I present to you now. So anyway, I'm going to continue now and explain Gul's theory to you how it works. Imagine here we have a lottery probability distribution over money. Let's assume that the outcomes have been ordered from best to worst. The highest is the best, the lowest is the worst. And somewhere in between is a certainty equivalent, the sure amount equally good. There it is. That means that a few, the best outcomes are better than that sure outcome, and others are worse. These are worse. If you get an outcome that is better than a certainty equivalent, then in a way you're a bit happy, you're elated. You think, oh, I ended up with something that's better than I felt beforehand. Disappointment is the other way around. If you end up with something worse than you thought beforehand, you're disappointed. Gul's theory is using this concept in the following formula. First, I write expected utility formula. Now, in his theory, with these outcomes, nothing will happen, but the disappointment outcomes will receive an extra weight, and a parameter beta, more precisely 1 plus beta, is the extra weight by which they are multiplied. Usually, beta is positive. That means that these are overweighted then. That means this person is paying more attention to the disappointment outcomes than to the elation outcomes, which is psychologically realistic. I should also say this beta is only one real number. So this theory generalizes expected utility by adding only one number with which it does something. In that sense, it's much simpler, more tractable than what we saw before. We saw before the true weighted utility theory adding a whole function f from the reals to the reals, much higher dimensional parameter than what we have here. Prospect theory also, there was a whole function w from the 0-1 interval to the reals. To the 0-1 interval. So again, a whole function, a much bigger parameter than here. So in that sense, the Gul theory is incorporating much fewer interesting new phenomena, but it's also incorporating much fewer uninteresting new phenomena. And again, there are pros and cons to it. But in general, having such tractability, such a simple generalization, there are many pros to it. And with the Gul theory, it's really very clever. And the big reason why it's so popular is that it is such a simple one-step generalization only, already capturing quite some interesting things. That's the clever thing of it. Anyway, always the weight should sum to and should normalize, so I wasn't complete yet. I should divide by all the weights to make sure that the weights sum to 1, that this is really a convex combination of the utility values, and there it is. So here we have the complete formula of disappointment aversion theory, the only new thing being overweighing the disappointment outcomes. Usually beta could also be negative, then you're underweighting, that means you're overweighting the elation outcome, but usually is empirically the prevailing pattern is beta positive disappointment aversion. Gul did provide a preference foundation, just as Chu also did it. And one preference condition was betweenness. I told you with Chu theory, I explained what betweenness means, and the Chu theory satisfies it. The Gul theory also satisfies betweenness. I told you Chu used one other condition that I did not define to get the preference foundation. Gul also adds one, well, other than Chu, of course, one other condition, and he gets the preference foundation. But again, no time to explain it here. When I explained this first version of prospect theory, by the way, a good, better version of prospect theory is yet to come. Anyway, the version I explained so far, it violated stochastic dominance, which was not good. A weighted utility was already better. It could satisfy stochastic dominance, but only on bounded intervals, never on the whole real interval. So that was a bit, but disappointment aversion is yet better. It just satisfies stochastic dominance everywhere. So that's a big pro of the theory. Further, I already said, it's very tractable, impressive. There's intuition to it, but there's a big drawback. And that, well, the theory is tractable in the sense of being simple with only one parameter, but its calculations are a bit inconvenient. It's implicit. And what I mean to say is, if you want to calculate what the certainty equivalent of a lottery is, you would like to know the preference function to calculate their values. But in this situation, if you want to calculate the preference function, you should already know the certainty equivalent. So you don't know where to begin. It's circular. In practice, you should try out some certainty values until by coincidence it fits together. Of course, with computers, we can do it more efficiently, but still, this is a quite inconvenient aspect. It's an implicit equation that defines the functional. Life is easier if there are only two outcomes, because then if there are only two outcomes, we need not know the certainty equivalent, because we can immediately say the best outcome of these two is elation, the worst outcome of these two is the disappointment. So then we can immediately go ahead, we can get an explicit formula. There it is. Where the worst outcome x2 is overweighted by the extra factor. Here we have an explicit formula. So then life is a bit easier. Some calculation to show how it works, that we can accommodate a Lie paradox, for instance. I'm gonna use utility. Let's take the square root utility function that's plausible, okay? I'm gonna take an extreme beta to illustrate how things work. Beta equal 4, that means 1 plus beta 5 is the overweighting of the disappointed outcomes. That's quite extreme, that's too extreme to be very realistic. But just to show you how the formula works, that you get a feeling of the theory. So we're going to accommodate the Lie paradox, the preferences again, using the new formula. And first we do the calculation, of course 10 million for sure. The disappointment aversion is just a utility, and the certainty equivalent is 10 million. That's trivial, we've seen it. Disappointment aversion is not doing anything here. The second lottery, there the disappointment aversion is in full force. Because here you see the zero outcome is the disappointment outcome is overweighted by a factor of 5. That means this number is going to be quite low, and we see it better if we calculate certainty equivalent only 7.9. 80% probability of 40 million, 7.9 million for sure is equally good. So this is quite low, and the disappointment is really hitting that lottery, punishing it, pushing it down. So here we have strong zero aversion, because zero is the worst, is a disappointment outcome. So it gives strong extra aversion. We see it in the formula. Now we go to the third lottery, this one. And again, the formula, you see there is a disappointment outcome. It's again zero, strongly overweighted. And again, especially if we calculate certainty equivalent, we see this only is already the certainty equivalent. So again, quite small. And this disappointment aversion is really making people pessimistic, decreasing the value of lotteries. And the same happens with the last lottery. Again, there's a zero outcome, overweight by factor 5. So we get a certainty equivalent of 0.09 only, again, quite small. Now, if you look at the whole pattern, we see, let's first look at the lowest preference. We see the third and the lottery are both hit strongly by that zero aversion, by that disappointment aversion, but they're hit in a similar fashion. So it doesn't really do much in that sense for the preference. And the 40 million is deciding over the 10 million. That's the preference. If we now look at the upper choice situation, we see the lower lottery is also hit by that zero aversion, but the upper lottery is not. So the upper lottery seems to be privileged in some sense, and that explains the preference reversal, why here you prefer the 10 million to the other one. That's why the preference switches, because the 10 million gets the privileged treatment of not being hit by disappointment aversion. So that's how this theory can accommodate the Lie paradox. And again, it's intuitively plausible, and I talk with many students, with you guys, and many experiments show indeed the moment there is such a bad outcome, people do overweight the disappointment outcome. Things like this are going on in the minds of people. Maybe it also looks, if you compare the comparison that we have here with the calculation that we did for weighted utility, they look very similar. Both of them just have an overweighting of the worst outcome in that complex combination. That's why we get zero aversion. So they look very similar, and they are, in many ways they are similar. They both satisfy betweenness, for instance. But a difference is that in the Gul theory, how much you weigh an outcome depends only on the outcome itself and not on the other outcomes of the lottery. It's only that F value that comes in here. In this theory, it matters in which lottery the outcome occurs. Is it a disappointment or is it an elation outcome? Like zero, maybe here 40 million is the elation outcome, but it could be a lottery where this is the worst outcome. Then it would be the disappointment outcome. And it would be overweighted by a factor 5, and now it's overweighted not just factor 1. So in that sense, this theory is formally different than the weighted utility theory by Chusong, but surely the theories are very similar in spirit. Now, next theory is coming. That's John Quiggin theory. He, in fact, fixed the problem of prospect theory. That will be in the next